Okay, so we got this bizarre limit. This is actually something we call a difference quotient for reasons that will be clear later. What do we always want to try to do with the limit first? Want to try to directly substitute. Now, what's weird about this one, though? There's x's and delta x's. Okay, so what am I substituting for? Delta x's. So as far as the limit is concerned, what's the variable here? Delta x, right? The x, yeah, the x is technically a variable. It's an algebraic variable, but not as far as the limit's concerned. As far as the limit's concerned, the thing that we're varying, the thing that we're going to make a substitution with, the value that's actually approaching something in the limit is the delta x, not the x, right? So if we plug in delta x equals 0, we're going to get 8 times x plus 0 is just x. So 8x squared minus 8x squared is 0 divided by 0. So sure enough, we get our indeterminate form. So we've got to do something with this, right? Okay, what do you think?
So is delta x not all related to x?
Delta x, whether it is or isn't, it's really not. It's really not, yeah. But whether it is or isn't, in this case, is irrelevant, because as far as the limit's concerned, the x isn't changing. Only the delta x is changing. So we should expect probably to get x's in our answer, unless for some weird reason they all cancel out or something. Right? The x's should be there, and we're all said and done. We're going to eventually make a substitution for delta x, but not the x. That's going to remain there, right? So we know we get 0 over 0. Which is more work. What's that more work look like, do you think? Yeah. I mean, that's gonna have to be, looking ahead, does everybody see that's gonna have to be the thing that cancels? Because that's what's 0 on the bottom. So we're gonna have to somehow get a factor of delta x on the top. Being able to see where that comes from right now might be tough, but sometimes in calculus, you just roll up your sleeves and get busy, and then eventually things start to happen. What do you think would be a good first step here to kind of get the ball rolling? No? I mean, could be expanded out here. Good. Yeah, we could expand out what's in parentheses. So we end up with, this is equal to the limit of 8 times, and what's all that going to become? If I do all this stuff right there, what happens if I expand out x plus delta x squared? What do I get?
Plus 2x delta x plus delta x squared.
Okay, and you guys all know that, right? Because all that is just an application of the binomial expansion, a plus b squared. Is what? You guys know that.
2x delta x.
Squared.
Oh, never mind, huh?
Okay, make sense? So in this case, a is x, b is delta x, right? Okay. So that's what we get when we expand all this out, minus 8x squared over delta x, as delta x goes to 0. There's a couple things we could do here. You need to talk to me. What are some ideas? So we could distribute the 8. Okay, that's fine. We could do that. So we end up then with the limit of, on the top, if I distribute all that, I'm just going to get 8x squared plus 16x delta x plus 8 delta x squared minus 8x squared all over delta x, as delta x goes to 0. Now what? Okay, good. So we get some horizontal cancellation. So they cancel the what? Well, what I mean by that, let me just, because we're going to say this a lot. So horizontal cancellation means cancellation by addition or subtraction, right? So what is 8x squared minus 8x squared? Okay, so they just go away. Horizontal cancellation means the terms disappear, right? So those are gone. Vertical cancellation cancels to what? 1 over 1, right? So good. So then we end up with the limit of 16x delta x plus 8 delta x squared. Ah, there you go, good. Okay, now we got what we wanted. All the terms left in the numerator have factors of delta x, right?
So if we cross stuff out, then we rewrite it without the crossed out stuff. We can't just like jump immediately from the 16x delta x.
To here?
Yeah, could we skip the just rewriting everything?
I think that would be okay to do, to go from there to there. Yeah.
Okay.
And then we get this, right? And so now if we let so now if we take our limit, what happens? Well, that term is going to go to 0, isn't it? And so we're left with 16x. Okay, one thing that we could have done slightly differently if you wanted to. Back up here at the beginning, in fact, let me just take, just going to grab a picture of this. So. Is this a big deal? No. I just want to make a point. Because it'll come up again later in calculus, this idea. Okay, could I factor anything out in front of the limit there? How many terms are there in the numerator?
We factor the 8.
I could factor an 8 out, couldn't I? Right?
8 times the limit of x equals to 0.
I could take the 8 out, I'd end up with 8 times this pink quantity minus x squared if I factored the 8 out, right? Okay, we have a property of limits that I just want to remind you about. We know that the limit, let's assume that the limit of f of x as x approaches a equals L, right? So if that's true, if I'm taking the limit of some constant times f of x as x approaches a, that's the same thing as taking c times the limit of f of x as x approaches a. Okay, how come? Because really right here, I could just split this up into 2 separate limits. Here's the justification. You'd never write it this way. This is way overkill. But we could break this up into the limit of c as x approaches a times the limit of f of x as x approaches a. Well, what's the limit of f of x as x approaches a? L. And what's the limit of c, that's a constant, as x approaches anything? What's the limit of 5 as x approaches a billion? 5. Right? There's no place to, how come? Because the graph is a horizontal line, but there's no place, here's a way to kind of think about it algebraically. There's no place to even make the substitution. So substituting for x means I don't do anything, right? So this just becomes c times L, right? Which is the same thing we get up here, isn't it? Right? So in essence, here's what you distill out of all this whole thing. It's a very simple concept. If there is a constant, you can factor the constant. You can, what we would say in calculus is pull it out in front of the limit. So we could just rewrite this as 8 times the limit of everything else. Now we'll write the whole thing out. But then we would just get the limit of x squared plus 2x delta x plus x squared minus x squared. It's a little bit easier to deal with over here than if we don't drag that 8 with us the whole time. See what I'm saying?
You just multiply it by that.
And then at the end, you just multiply by the 8. So what would have happened? At the 8, you would have ended up, instead of having that 8 being distributed through, wouldn't you just end up with, you'd end up with a 2x delta x, x squared plus 2x delta x plus x squared minus x squared. So the x squareds would have canceled, right? And then when we factored in, that would have been a 2 instead of a 16. Everybody see that? So our final answer, instead of being 16x, the limit part would have been 2x, but then there's our 8 out front, right? You see how that could be advantageous? What if instead of an 8, that was 113/7 or something? You don't want to drag that. Just factor it out front and multiply it through at the end instead of having to drag that all the way through all your work and muddy it up, right? Okay? You'll get used to that idea. Okay, so what else? Special limits. So last issue. So how do we deal with trig limits? The third one's kind of a weird one. We won't deal with that for a while. That will, I mean, in fact, I don't know if that's even covered on the AP test. I'll have to look. I don't think it is. Only two I believe that are will be the first two. Okay, so these are ones, for now, that's all I really care about. I'll make a list of this and I'll put it on Moodle of all the limits that we have, that, all this stuff, and then you can kind of have that available as a PDF to look at and memorize some stuff. Really, there's been nothing to memorize so far, just some techniques. There's nothing, in those you'll just remember, that you don't have to write anything down. Here are some, though, to remember, that you kind of have to just commit to memory. The limit of sine x over x as x approaches 0 equals 1. There's a really cool way to prove that I'd like to show you using a kind of a geometric proof. It's called the squeeze theorem, and there's a cool geometric proof you can do that I'd like to show you, but I'm not going to do it now. Just I don't want to take the time. That might be something we'll come back and look at after the AP test. There might be like 2 or 3 things.
Isn't 1 minus cosine x, is that the same thing as sin x?
No.
No?
No, 1 minus cosine squared would be sine squared. But it's not the same thing. There's a way, I'll show you a way, not right now. Just kind of remember these, but I will show you a way that you could easily use a quick little trig proof to get from one to the other if you just remember one. That's the way, I never remember this one. I always just derive it for myself from this one. But you'd probably be better off for now just memorizing it. Okay, but I'll show you that trick. These are two that aren't obvious. They're ones that you'd have to prove. You can't just get these in some convenient way. There actually is a little bit of a proof involved. And it's really cool, but for now, just take it on faith that number 1 and number 2 work.
So if we use that on the AP test, they are expecting us to have that number.
Oh, yeah, exactly. They're gonna expect you to know both of those limits.
Okay.
And the one you use 90% of the time is this one. This one may or may not show up even once on there, but it might. It might, okay? And of course, if we did try to evaluate these directly, everybody see I get 0 over 0 in both cases. So then our goal is, when we're doing trig limits, and we always want to check and see if we need to even do anything. Maybe this is a quick and easy one where direct evaluation works. What do we get if I try to evaluate this at 0? What's the tangent of 0? Remember, tangent's just sine over cosine. That's how I always think about it. Sine of 0 is 0. Cosine of 0 is 1. So you end up with tangent of 0 is 0, isn't it? So we do get 0 over 0, unfortunately. So there's more work. Well, how do you get the more work this time? This is different, right? This time we're not going to get factors that cancel. What we have to just do is we have to use our trig identities and our trig relationships to coax out these known special trig limits. And that's how you eliminate the indeterminacy. Instead of having like an x divided by x, you're going to end up having somewhere in here we might have a limit of sine x over x as x approaches 0. Well, there's the indeterminacy. That goes to 1 though, okay? This is a pretty simple one. What do you think we probably want to do in this case with these trig limits?
Split the things.
Okay, yeah, what's a good idea is always with the trig ones is to write the compound or the complex trig units in terms of the base trig functions, right? Just sine and cosine. Okay? Well, most of our trig identities are in terms of sines and cosines, and both of these special limits are written in terms of sines and cosines, right? So we could take the limit of tangent x over x as x approaches 0, and how am I going to write that then? The limit of
Sine over cosine x.
okay, so the tangent is sine x over cosine x, right? So dividing by x is the same as multiplying by 1 over x, right? Everybody agree? So does everybody see then that I could just write it like that? And that's something that I would say is probably the first step, just to jump right from there.
Didn't you simplify that as cosine x squared?
How?
The x cosine x.
No. No, because this x, see, this is the argument of the cosine. It's buried inside the cosine function. This x is not, so they don't interact at all, right? Everybody see that? Like if you try to do something like cosine x times x, that is not equal, what's it not? It's not equal to cosine x squared, because that one's inside the function. Right. What can we do with that, though? We can just, and we're taking the limit as x goes to 0. Can we break that up into a product of separate limits that make more sense? Yeah. Can we reorganize that? We got an idea. Raise a hand if you got an idea. See, I was some new participants today. Somebody else, jump in here. Help me out. And my goal is, if I can, these are the ones that I know.
Wait, can you repeat the question?
Yeah, so what I'd like to do is, I'd like to be able to write this, you fill in the blanks. I want to be able to write this as a product of limits where, like if I could organize it so I could see a limit of sine x over x in there, I know what that goes to. As x goes to 0, that goes to 1, right? We got that though, don't we? I mean, I've got, how many things do I have mixed in here? How many factors do I have in my big quotient here? I got a sine x, an x, and a cosine. I got 3 things that are being multiplied and divided, right? Can I reorganize that so I can see the quotient of those 2 times something else? Well, sure, right? Sine x divided by x times cosine x, isn't that the same thing as sine x over x times 1 over cosine x?
Yes.
I can just split that up, right? So I've got the limit of sine over x times 1 over cosine x as x approaches 0. So technically, what I'm really doing here then is I'm just going to split this up into separate limits. We have a property of limits that says if I have the limit of f of x times g of x as x approaches something, I can write that as the limit of f of x times the limit of g of x separately, right? We can just split those up. Okay. So I can think of this then as being the limit of sine x over x as x approaches 0. Let's just put that in brackets to separate it. We don't need to. Times the limit of 1 over cosine x as x approaches 0. And what are those equal to? What's the limit of sine x over x as x approaches 0? 1, because that's our special limit, right? So that's equal to 1. This one is equal to what? We'll directly evaluate. As x goes to 0, you already told me cosine x becomes 1, right? So I get 1 over 1. I get 1 times 1. So my final answer is 1. Okay, so what was our strategy? We just wanted to reorder this thing so that we were able to get this limit as a factor in our limit, right? We're going to end up with the limit of sine x over x times some other stuff. But that's the one that caused the indeterminacy to go away. That's what was responsible. It was sneaky, but that's what was responsible for the 0 over 0 nature, right? The indeterminacy. Okay? Let's try another one of those. How about... Well, okay, let's do this one first, and then we'll do another trig. I feel like the trig ones, maybe we need a few more examples. Okay, so what about this? That's trying to be what limit? Sine x over x. Doesn't have to be an x. Could be anything. Like if, in this case, being as we're using x's in there, I could say the limit of sine theta over theta as theta approaches 0 is 1, right? So what's theta trying to be here? Well, I can see where you'd say that because there's an x on the bottom. But the problem is, it's easier to change what's being multiplied by that x than it is to the one that's outside the function than changing what's being multiplied the x inside the sine function, right? You get that? That the sine function 4x is the argument of the sine function. It's pretty hard to change that, to do anything, like, you could. We could do something like, for example, we could say, if we had the sine, hypothetically, of 2x, well, we could use the fact that the sine of 2x equals 2 sine x cosine x from last year, right, trig idea, to rewrite that in terms of x's instead of 2x's. But that's not easy to do, right? When you want to change the coefficient of a variable inside a trig function, you got to go back and use all those double angle formulas and half angle formulas, and think what you'd have to do here. Sine of 4x, we'd have to break that into the sine of 2x times 2, right? So that would equal, just look what this, I just want to make this point once, so you'll run for the hills anytime you ever, you don't want to do this. You don't want to go where I'm going right now, if you can all avoid it. Sine of 4x would be 2 times the sine of 2x times cosine of 2x. Well, what's the sine of 2x? 2 sine x cosine x, right? So we're going to get 2 times 2 sine x cosine x times cosine of 2x. Yikes. That's going to be cosine squared x minus sine squared x in parentheses. That's a mess. Horrible mess. Right? So we're going to leave the sine 4x alone. Everybody see where I'm going with that? We don't want to mess with that, right? Okay, so let's start this thing over again on the next page. We'll abandon that. Okay, so what do we want to probably change instead? Now, I'll write this up here again. We had a sine, call it what you want. I'll call it theta. Sine theta over theta in the limit as theta approaches 0 is 1. That's our special limit. Well, what are we probably going to let theta be here?
4x.
4x. Right, we don't want to change that, do we? Right? All we got to do is get this in the form sine of theta over theta equals 0. So what would it be much more convenient to have on the bottom than an x? Absolutely. Yeah, you multiply by 1 in the form of 4 over 4. Is that what you're saying?
Yeah.
Yeah. Yep, then you move it out front, exactly. Yeah, you're seeing it, good. So we could write this as then the limit of 4 times sine 4x over 4x, right? That looks pretty good. What's our theta now? 4x, that works, doesn't it, right? So this matches the pattern almost. We have the sine of theta over theta, right? So you can see right here, here are my thetas. Where am I missing a theta though?
4.
Well, that's okay, but what's the other part of this? It's the sine of theta over theta as theta goes to 0. The limit, meaning this part right here, right? Okay, but let me ask you something. As x approaches 0, what does 4x approach?
0.
Easy. Just add a 4 there.
You can just do that?
Sure. Why can we do it? Because the two are consistent. If one is true, one necessitates the other. If one, then the other. If x goes to 0, then 4x goes to 0. Okay? And maybe that's worth writing. I never do. But you could make that statement. If x goes to 0, then 4x goes to 0, so therefore you can add the 4. Yes?
What if it's not 0?
Okay, then, but it has to be because that's the limit we're using. Yeah, so you're right. Then it would be a problem, but it is, and so we're fine.
Then we would
Yeah.
get rid of the whole outs.
Well, then we'd have some problems beyond that. I mean, that's, not all trig limits are easily resolvable. I mean, this is one that is, right? So then, Kirk's suggestion was now we've got the 4, which is a constant multiplier, right? Inside, we call that a scalar multiplier. It's fine, no big deal. We just pull that 4, you just pull it out front, right? It's a constant factor, so we pull it out front, and we end up with 4 times the limit of sine 4x over 4x as 4x goes to 0, and everybody agrees that's 1, right? end up with 4 times 1 equals 4. Okay? How about, I'm gonna pull up another, well, I'm gonna skip this for today. Okay, question? Yep.
Were we to write down the AP test, would they make us prove that the limit of 4 as x approaches 0 has to be 4?
I don't think so.
You know, we could write that down.
I think that would be fine the way we wrote it.
Okay.
It seems,
Given that
it seems.
4 times 1 equals 4.
Say it again?
Do we have to write the 4 times 1, or can we just say, okay, that equals 4?
I think you could just, you could even do this, you could even probably just say,
Are you laughing?
like that.
Yeah.
Or I bet even just the way it was, it's fine. I mean, you'd rather be, so, talking AP test, if you're unsure,
Write it out.
you write it down, but not if it's gonna take too long to do. If it's quick, something quick, then fine, but otherwise, it's hard to finish. It's very hard to finish. The AP test, by the way, I don't mean to scare you, and I just mean to kind of give you this, because I'm not gonna do this, I'm not gonna kill you guys to get ready for one stupid test. I mean, it's, I'm giving about 30% as much homework as this guy recommended. I'm just not gonna give you,
Me.
well, it's a little different approach. Well, it's a different school. You have 90 minutes a day in calculus.
Oh my god.
They only have 4 classes, students only have 4 classes. So it's a different deal. Yeah, so it's a way different deal.
So they
you-
have
so-
every other day.
Say it again.
Do you ever teach you on half block?
But yeah, it wasn't a true block. I taught in McMinnville, when we had a trimester schedule, we taught 70 minutes a day, which was, and all my kids always passed the AP test. Everybody passed. But this guy has everybody get 4s and 5s. And I had some 3s. So, but that was a way different deal. I mean, it was a lot better for students than this. They had 5 periods a day, so calculus was 150 your day. That eliminates the number of homework classes you have. We had all year that long calculus that way, so it made sense. We had great scores because of that. But it is just, everybody should take the test. It's really, I think you should, just as an experienced thing, but I want you to also realize that calculus statistically is by far the hardest AP test. Nothing else is even remotely close to it. The number of people that pass the calculus test, like in English is typically pretty high. History classes is pretty high nationally. Calculus is something else. I mean, it's really low. It's really low. But I also think, but I also think that a lot of calculus classes, just are not taught very well. And it's not that hard to do. I had those. There's better calculus teachers than me out there. This guy, I'm sure, is better teachers than I am. I was like the last couple of years I taught it, everybody passed. Out of 40-some kids, they all passed the test. So it's 3, 4, 5. 3 is passing. Almost all schools will take a 3 for full credit, but there are some schools, like I know Stanford wouldn't take a 3. And then there are some schools that wouldn't take a 3 for like instead of giving you 10 credits, they give you 5 credits or something. But 4 or 5 is accepted. But do kind of take this. Take it seriously. Work hard. Mostly not because of this test. I realize there's some college credit here for you, but here's the honest truth also, is that most people that pass the AP test, most of my students that passed it, still went on and repeated differential calculus in college, which is not a bad thing. Differential calculus will be so simple for you guys. It's a guaranteed A. I can absolutely guarantee it that if you show up for class and do a modicum of the homework, it's going to be the easiest thing you've ever done. We're going to do everything in here. Maybe harder than it'll be next year. So that'll be a piece of cake. It's not always, getting this credit may not always be something you want to do anyway, It's jumping into higher level calculus as a freshman when you're away from home for the first time, you're having to, there's all these things. It's not bad to have an ace in the hole where you know you're going to be able to tag your GPA and kind of ease into things a little bit. So, I'm just saying this stuff, so don't make this like the end all be all. Like if you don't pass this test, it's the end of it. It's not, we'll do our best. I'll do everything everything that I need to do to get you ready for the test. And I know exactly what that is. It's not like there's any mysteries out there, it's just calculus. But you guys also have 7 classes instead of 4, you have things going on, and I refuse to give you 90 minutes of homework in that. I'm just not gonna do it, because I don't think that's reasonable to do, you know? So, anyway, if this is a super important thing for you, which it might be, and that's fine, then I can recommend some other things that you can be doing as we approach the test to get some additional work on it, I think. Not to sell things short, I mean, we're gonna be fine, but, yes, sir.
So is this actually calculus, or is this just leading up to it?
This would be considered calculus, yeah. Yeah, it's not, later on in the class, you'll say, oh, just that limit stuff, that's no big, that was before we started doing differentiation and integration. That's really mostly the calculus. When we talk about calculus, those are the 2 things that you mostly are referring to. But this is a part of it, yeah. Really technically it's probably pre-calculus, but it's taught in the calculus class. Okay. All right. How much time we got? 12 minutes. Why don't would you rather work or go through another example? Want to work a little bit? Okay, work.
So what happens, like, when you get the hard calculus, just bigger problems?